Okay, up to this point, we've been developing finite difference approximations to the first derivative just using kind of an intuitive approach. That gave us these three different expressions, forward, backwards, and a standard difference expression. And we saw when we did the example that these will give us varying degrees of approximations, and sometimes they work, sometimes they don't. Forward difference, for example, won't work for the last data set that you have, the last point. Um, and so it's kind of developing. We're coming together with some ideas, but we really don't have yet a good way to characterize the error that results from this approach. And so what I'm going to do is to introduce a method that will allow us to get a handle on the error from finite difference approximations. And we'll do it by going back to the notes from calculus class and using this concept called Taylor series from calculus. And this is Taylor series, and I'm sure everybody remembers that. This is, I think, at first glance, somewhat cryptic, but it's actually really pretty interesting the way that this works. Taylor series is basically an approach for predicting the future, um, or for looking ahead in time or space. And so here's how it's going to work. This is, let's say we have something like this. We've got a function, and this is f of x, and this is point A right here. Well, this is f at a plus delta x. So we'll, we'll go out here delta x, and right there, that's a plus delta x. So the function at a plus delta x is right there. And what this is, Taylor series is doing is allowing us to get the value of the function f at this point when all we know is the function at a. So if we know everything about the function at a, if we know the value of the function, and that subscript or superscript there means the derivative. So k of 1 is the first derivative, and 2 is second, and so on. So if we know the function at point A and we know all of the derivatives at point A, then we can use Taylor series to predict what the function is out here at a plus delta x. Okay, so that's kind of cool. It's given us a forecasting ability using the function and its derivatives. And so conceptually, I think that that's appealing. And let's see how it works. And so series are a nice compact way of writing a much longer expression. And in this case, the series goes out to infinity, so it would be a very long expression indeed. But what we'll see is that when we use this expression, we'll actually truncate the series, so we only use a few of the terms. So let's expand it out. So I'm going to say that f at a plus delta x is equal to, and it's going to be this thing. So I'm going to let k equal 0. So when k equals 0, we've got 0 here in the denominator, so we'll just say that that equals 1, and f at, with a k subscript, that'll just equal f at a. Okay? And now, so this is k equals 0. And then we'll add to that k equals 1. So when k equals 1, the denominator is 1. This is delta x. That is delta x to the first power, and it's the first derivative. So this is delta x times the first derivative at point A. And so it's k equals 1. And then for k equals 2, we have delta x squared over 2 factorial, which is 2, and it's the second derivative at a. And then for k is equal to 3, it's delta x cubed 3 factorial, which is 3 times 2 times 1, which is 6. And then it's the third derivative at a. And then the fourth term would be, I guess, well, let's go ahead and do it. Delta x to the fourth, 4 factorial, which is 24. And then the fourth derivative of f, like that, at a. And then we could keep going, but we don't really want to. Oh, I've had enough. I've run out of room. And so I'm going to say, well, I'm going to chop off all the rest of the stuff from k equals 4 or k equals 5 and k from k equals 5 to k equals infinity. And so I'm going to just cut that off, and I'm going to say all of that has order delta x to the fifth. Okay, because I've got delta x to the fourth here. The next term would be delta x to the fifth. Okay, so there's the Taylor series written out, and you can see this kind of extrapolative character of the Taylor series, because what it says is that f at a plus delta x, f at that point, here's the starting point. So there's the starting point right there. And then this is the f prime of a is the slope. So the slope at f of a is equal to that. And the slope times delta x. So if that's delta x, the slope times delta x would be this much right here. Okay, so there's f at a, and if we add to it this term, then we get right here. I'm going to erase some of this stuff here. So after the first and second term, we're right here. Okay, that's the value that we're after. So we're getting a little bit better. Now this next term here, it's the second derivative, and you can see that for this curve, this is the curve that we're working on, and the second derivative is negative, and we take that multiplied by delta x squared over 2. That's going to give us also a small increment in f, and what that'll do is that will have a magnitude that'll be about like this. It's going to be about this big, and it's going to be negative, so it's going to drop us down from this point to right here. And so you can see that we're getting closer to this value right here, which is our true value. And when we add in this next term, it's going to overshoot a little bit, but it's going to get progressively closer and closer. So each one of these terms gets us closer to the true value, and at least in this case, one term overshoots, the next term undershoots, and it converges on the right answer. And then at some point we say, well, we're close enough, and we're going to truncate all the rest of the terms, and that gives us this order of the approximation of the series. So here's the expression written out in typeset. So this might be a little bit easier to read than my handwriting. And in this case, I only wrote out the first, through the third derivative, and so the series is truncated right here. So these are all terms from the series here, and you can see we've got 4 of them. There's 1, 2, 3, and 4. And then the one that includes the fourth derivative and includes delta x to the fourth, we're not including that. So the series is truncated right here, and our placeholder for all of the terms that are missing is shown here. What this means is that, if the Taylor series is taken out with an infinite number of terms, then it's exact. It's exactly right. But because we're truncating it, we have some error, and the error is going to be proportional to delta x to the fourth. Okay, so we're starting to get a view of what error means, at least in this context of Taylor series. And so that'll end up being an important factor when we turn this approach to understanding finite differences. Okay, so let's go ahead and try this out. Here's the Taylor series that we just saw on the bottom of the page, and we're going to use this as f of x, and we're going to start at x equals 1, and we want to use the Taylor series to determine the function here at x equals 1.5. So let's just say right here that's 1, x equals 1. So this is our starting point, and we have a delta x of 0.5, so there's 0.5, and this value right here is 1.5. And so because we start with this function, we know what the exact value is. That should be what we're after. Okay, and so let's use this Taylor series approach to try out the approximation. And the advantage of doing this is we know what the exact value is. So we know what the true value is, and we can try first this term here, and then this term plus this term, and the first three terms in the Taylor series, and see how the approximation is improving as we do that. Okay, so here's what we do. This is the general Taylor series expression, and what I've written out here is this top expression with our examples substituted in. And at first, we're just going to substitute in the values for x and x plus, well, actually this right here would be a, and this would be x equals a, and this would be x equals a plus delta x. Okay, so right there, that's f at a plus delta x. Okay, a is 1, delta x is 0.5. And then here's the Taylor series, this term here, and I have delta x is right there, and a is right there. Okay, now I'm going to expand it out. There's f evaluated at 1, there's f prime evaluated at 1, fw prime, double prime evaluated at 1, and there's the delta x squared, and so on. Okay, so that's how we're going to do it. Now what we need to do is calculate these derivatives. So I did that here. So if f of x is equal to 1 minus e to the minus 2x, then the first derivative, these are pretty easy. That's going to go, and we get 2 e to the minus 2x, and f double prime of x is equal to minus 4 e to the minus 2x, and triple prime is this minus 2 comes down, so we'll just get 8 e to the minus 2x. Okay, and that's what's written here. We can also see there's the fourth derivative. Okay, so with this in mind, then we can go from here and substitute in the derivatives. So this term right here is is given right there. That's this term where we substitute in for x the value of 1. Okay, so that gives us that expression right there. The next term right here, that's the second expression. So that's this one right here, which is 0.5 times the first derivative. First derivative is right there. So that's right there, 0.5 times the first derivative. And then the next one here is 0.5 squared times the second derivative. There's the second derivative. So there's the next term. And then it's 0.5 cubed times the third derivative divided by 6. And that's that term there. Okay? So what we see then is each one of these terms is just something we can punch into our calculator. There are no variables anymore. So we can calculate what that value is, and so on. We can also calculate what that value is. That's the exact value. So we can see the exact value is 0.95. So right there, that's 0.95021. And then we can calculate each one of these expressions, or each one of these terms. The first one is there. This one is there, and so on. Okay? So that's how we get the values. Now what I want to do is go and see for the first term, we want to compare and the error that we get for the first term compared to that one. And then we'll take this first term and add in the second term and compare that sum to the exact value. And then we add in this next term and compare that sum, and so on. Okay, so hopefully we'll progressively get better. Okay, so we'll take a look at that in just a second.